All right, let's jump right in. Today we're exploring one of the absolute pillars of medicine. It's a field whose name literally translates to the study of suffering. And it's the science that's all about asking why we get sick and how it all happens. We're going to delve into the incredible world of pathology. And if you need any proof of just how vital this field is, just listen to this quote from Sir William Osler, who's known as the father of modern medicine. He said, "Your practice of medicine will be as good as is your understanding of pathology." That's not just some fancy line. It's literally the foundation that connects a diagnosis to a treatment. It's everything.
But what does suffering even mean in a scientific sense? I mean, how do doctors take this abstract idea of being sick and turn it into something they can actually study, something they can fight? Well, that's the core mission of pathology.
At its very heart, pathology is the scientific study of what changes in our bodies, both in structure and in function, when disease hits. You can think of it as the crucial bridge connecting the basic sciences, like anatomy and biology, with the real-world, hands-on practice of treating patients. It makes the idea of a disease something real, something we can actually get our hands on and understand.
But we didn't always have this understanding. Not by a long shot. It was a really long journey. And it started with ideas that, looking back, seemed kind of wild. So let's trace that journey, starting with a theory that dominated medicine for almost 2,000 years. For nearly 2 millennia, can you believe that? Brilliant thinkers like Hippocrates and Galen were convinced that our health depended on a perfect balance of 4 body fluids, or humors: blood, lymph, black bile, and biliary secretion. So, the thinking was, if you were sick, it's because one of these humors was out of whack. It was their best attempt to explain illness, but it was all focused on these abstract fluids instead of the body's actual parts.
Then, everything changed. The first huge revolution came from a guy named Giovanni Morgagni, and he completely flipped the script. Instead of just theorizing about invisible fluids, Morgagni conducted over 700 autopsies. He carefully connected the dots between a patient's symptoms when they were alive and the visible physical changes in their organs after they died. This was a total game changer, the birth of what we call clinical pathologic correlation. He proved that diseases live in our organs, not in some mysterious fluid imbalance.
So, Morgagni took us from humors to organs. But the next great leap in understanding? It was about to get even smaller, way smaller. All thanks to a piece of new technology, we were about to zoom in from the whole organ to its tiniest building blocks. And this is where Rudolf Virchow, the father of cellular pathology, enters the scene. Using a microscope, he put forward this radical idea. Disease isn't really a problem of the whole organ. It's an alteration of its individual cells. His theory boiled down to 2 simple but profound ideas. All cells come from other cells, and disease is just what happens when those cells go wrong. The root of suffering was now officially located at the cellular level. Okay, so once we knew that disease was a cellular thing, pathology needed a game plan, a systematic way to investigate any disease. You can think of it like a medical detective's playbook, a structured approach that we still rely on today as the foundation of disease study. And this right here, this is that playbook. You can see how pathologists trace the path right from the initial cause, the etiology, to the how, the mechanism of the disease, which is called pathogenesis. And all of that leads to the changes we can actually see and measure. It's a system for answering 3 essential questions: why, how, and what. It all has to start with the most basic question a doctor can possibly ask. Why? Why did this person get sick? What kicked this whole thing off? In pathology, we call this etiology. It's all about finding the root cause, the culprit. Is it something genetic, something literally written into the patient's code from day one? Or is it something they acquired, like an infection, a toxin, or an injury? Figuring out the why is absolutely crucial because it shapes the entire plan for treatment and prevention. So, once you've got your cause, the next logical question is all about the chain of events. How did that initial spark ignite into a full-blown disease? And that's pathogenesis, the how. It's basically the story of the disease, the step-by-step sequence of events at the molecular and cellular level that takes you from the initial trigger to the final illness. Understanding this pathway is what allows scientists to create drugs that can jump in at just the right point in that chain to stop the disease cold. All right, so we have our culprit, and we know their methods. Now, what about the physical evidence? What changes, what clues has this disease left behind on the body? That evidence is called morphology,
The what? These are the actual physical alterations in tissues and cells, what we call lesions. They're like the fingerprints of the disease. And examining these changes, whether they're gross changes you can see with the naked eye or tiny ones you need a microscope for, is often how a final, definitive diagnosis is made.
Now, this whole framework isn't just theory for a textbook. Let's take a look at how it works in the real world, where pathologists are right on the front lines, giving critical answers that guide doctors and save lives every single day. So let's check out two scenarios. Over on the left, you've got a classic high-stakes technique, the frozen section. A surgeon is in the middle of an operation and needs to know, right now, if a tumor is cancerous. So a piece of it gets rushed to the lab, flash frozen, and diagnosed in minutes. That diagnosis guides the surgeon's very next cut. Then on the right, you have its 21st century cousin, telepathology, where a digital image of a slide can be beamed across the world for an expert to look at.
But even with this amazing tech, we get new kinds of challenges. One of the big ones in telepathology is something called sender's bias. Think about it. The expert pathologist on the other side of the world can only diagnose what they are shown. If the person at the microscope doesn't pick the right areas to send images of, well, crucial information could be completely missed. It's a huge reminder that technology is an amazing tool, but human judgment is still absolutely essential.
So we've gone from humors to organs to cells. This whole journey has been about zooming in closer and closer to the real root of disease. And now we're taking the final leap into the actual code of life itself.
This slide just captures it perfectly. We've moved beyond just the cell's structure. We're now investigating the chromosomes inside the nucleus, and even deeper, down to the sequence of our DNA. We are literally reading our body's blueprint, looking for the tiny errors that lead to disease.
And this leap forward happened incredibly fast. I mean, just look at the speed here. 1953, Watson and Crick figure out the double helix. Just a few years later, we get the right human chromosome number. Then in '83, PCR is invented, which lets us basically photocopy DNA. And by 2003, the entire Human Genome Project is done. The pace of discovery has been just staggering.
So think about where we started this journey, with vague ideas about imbalances in imaginary fluids. And today, we can read the 3 billion letter code that builds a human being. We can pinpoint the exact typos in our genetic code that cause so much suffering. And all of that leaves us with the most incredible and profound question of all. Now that we can read the blueprint, can we finally learn how to rewrite the story?